So another aspect of 1D steady-state conduction with no generation is composite materials. So composite materials often are modeled using this circuit analysis approach. So composite materials are used very often in applications and vehicles, airplanes that you're very familiar with. So this is just showing the Boeing 777 and just different components of it and how different composite materials are used to make up its structure. Another example is a thermal interface material. So with a chip and a heat sink, you want to put a thermal interface material in between it to make that thermal interface resistance lower, for all the good reasons that we said before. So in this structure, you have carbon nanotubes, these fiber-like structures that a lot of researchers have been looking at over the years, and they're starting to show up in products. They have very high thermal conductivities in the axial direction. So you have forests of these carpet-like structures sticking up that are impregnated with a polymer material. So if you wanted to know what the effective thermal conductivity of this material is, one way to do that is to represent it as an equivalent resistance. So what we would have here is two heat flow paths in parallel. Heat can flow through the carbon nanotubes and it can flow through the polymer material. Both of them have different thermal conductivities, but you can come up with an effective thermal conductivity by treating them as resistors in parallel. So here's a cartoon from your book that shows an example of a composite material or composite wall where we have 1, 2, 3, 4 sections. So there's two different ways that the book shows that you can represent a circuit network. And there's some latitude that the engineers afforded when using this analysis technique to set up the problem. So here, in the first approach, we take material E, which has an area in the direction of the heat flow that's twice material G and F. And then material H has the same area as material E, which is twice material G and F. So one way to represent this circuit is to have a resistor for material E. Then for material F and G, you have two resistors in parallel. And then these parallel resistors are in series with the other two materials on both of their sides. So here we have two resistors in parallel. This can be lumped into an equivalent resistance, and then we have three in series. So you can do the same problem and come to the same result by dividing material E and material A into two materials with the same properties. So we can take this line, we can extend it this way, we can extend it this way. So that now we have 6 sections, so that we have 3 circuits in series on the top section and 3 circuits in series on the bottom section. So we didn't do any magic here because these 2 circuits are the same as this one circuit. For this one circuit, it's L over Ka, and for these 2 circuits, it's L over Ka divided by 2. So we just divided the area by 2, divided the resistance basically by 2, and broke it up just so we can represent our circuit in a different way. So that's how you would approach a composite material problem. You'd identify the problem, look at the paths that heat could flow within the composite. Usually if it's composite, it has 2 distinct material structures that have distinct properties, so they would make up their own separate resistive components. But ultimately what you're looking for is an equivalent resistance. And like I said with the example with the carbon nanotube polymer mix, sometimes the problem will be trying to find out what an effective thermal conductivity is. So here we're focusing on finding out what a total effective resistance is, but if you look closely at the representation of resistance as it shows up in Fourier's law, then you can see that you could relate resistance to thermal conductivity. So if you find the effective resistance or the total resistance of a composite material, then you should be able to use that to find an effective thermal conductivity as well. So what if, with these two materials that are in parallel, what if their thermal conductivities aren't equal? So we already really said they're not equal. But let's think more about that. Taking it even further, what happens as the difference between these two thermal conductivities increases? So material Kg or G has a really high thermal conductivity, and material F has a very low thermal conductivity. And that's actually a system that's very close to the carbon nanotube composite system. Carbon nanotubes have thermal conductivities that can be as high as thousands of watts per meter Kelvin, and polymers have thermal conductivities that are usually fractions of a watt per meter Kelvin, maybe around 0.5 or 0.3. So what happens in this case? Well, if you have a high thermal conductivity material here and a low thermal conductivity material here, that means you're going to have a high thermal resistance here and a low thermal resistance here. If you think about circuits and the path of least resistance, when heat tries to pass from here to here, it's going to, like all of us, humans and natural systems, we tend to like the path of least resistance. So the heat's going to follow that path of least resistance as well. So it's possible, when this thermal conductivity difference is great, for two-dimensional effects, heat flow effects, to show up in a problem like this. Meaning that this line between the two materials would no longer be adiabatic, meaning that it's possible to have heat flow across that line. But that said, we're talking about it so that we can understand the limitations of applying a resistive network model like this to a composite material. So you can still choose, even if this thermal conductivity is high and this one's low, you can still choose to represent it with this resistive network model. But if you're out in practice making a design, you have to be aware that when this difference between thermal conductivities gets really large, that the accuracy of your analysis will start to decrease. So it'll become less accurate. So I might suggest, even if you had a problem like this in real life, you first may want to work it using an equivalent circuit approach, but then you may want to use a more rigorous technique that handles two-dimensional heat transfer, and then compare the results just to see.